Okay, good morning. Good morning, everybody. How are you doing? It's okay? All right, so this is the last lecture of this week, right? So the other things which remain will be hands-on exercises. So what I would like to do today is finish where we left off, talking about comparisons between groups and hypothesis testing. And then we will talk about sample size calculation, because, of course, this is one of the kind of bigger questions, but we need to know everything we talk about to even be prepared to discuss sample size. So it's getting more technical, so let me make sure we review what we talked about yesterday, just to refresh our memory, right? So if I maybe start from the beginning, right? So we are focusing on statistical goal number 2, where we want to compare averages of protein abundances between populations, right? So again, we have these constants, which are the mean abundances of a protein in one population versus in another population. We're working on the log scale, therefore we want to consider differences between the groups. We assume that these constants exist. We don't know, and we will never ever know their values, but they exist, and our question is, are they the same or are they different? Because if they're different, it means that the protein is up or down regulated. And then we select subjects from the populations, we include them in the study. And again, the abundance of proteins in the selected subjects is unknown because we cannot see it. What we can see is the measurements from our technologies. So if we talk about mass spectrometry, it's intensities of spectral features, right, or chromatographic peaks. And so then what we will do, we'll take summary of what we observe. We will describe the statistical properties of the summaries, and it would require some assumptions. And given the data and given the assumptions, we will attempt to make conclusions about what we do not see and what is of interest to us. And these conclusions are statistical inference. And so in terms of experimental design, we have to be very careful to avoid bias, where what we see is systematically different from what we are interested in, and also minimize inefficiency. So we want to minimize the variance. And so in terms of sample size calculation, this will be quite important for us. So we will get back to that. And so what we did, so we work on the log scale, right? And so we constructed a quantity which we can think of as a signal-to-noise ratio. So the signal is what the difference between the groups, our summary, and the noise, the denominator, is the uncertainty associated with the first mean and the uncertainty associated with the second mean, right? And remember, this uncertainty essentially was represented by how much variability we will have between the means if we kept collecting data of the same sample size, right? And so the larger the sample size, the more similar to each other the means would be. The smaller sample size, the more different it would be. And so mathematically, this is described in terms of the variance of the sampling distribution of the mean, right? So if we keep collecting means, the histograms are the sampling distributions, and the square root of this is the standard error of the mean, right? And so standard deviation tells us how much variation we have in the population. Standard error tells us how much uncertainty we have in the mean. And so standard deviation will never go to zero, kind of, if the sample size increases, but standard error will go to zero as the sample size increases, because we narrow more and more to the same value. Okay, and so what we did then is we wanted essentially find a way to decide how large this signal to noise should be to claim that this difference is larger than the noise, right? That the signal is larger than the noise. And so this is where the assumptions are important. And so we assume that our data are distributed according to normal distribution. And we also assume that each data point is independent, meaning that whatever happens to person number 1 has no implications for person number 2. And so in biology, it's often the case. However, if we have things such as batch effects or some other experimental artifacts, this can become a problem. Now, if our data are not exactly normal, we can claim central limit theorem and say that even though the actual data are not normal, the distributions of the means are approximately normal. And so if we make these assumptions, then mathematically we can describe the range of values that the signal-to-noise ratio will take if, in fact, there is no difference between the groups. And so this range of value is described in terms of a probability distribution. So this is a student distribution, which looks very similar to the normal distribution. It varies around 0. We lost 0 somehow on my slides. But essentially, it would be distributed roughly around 0, and we can describe this mathematically. So we don't need to actually repeatedly collect data. And then we said, okay, since it's a probability distribution, the area under the curve corresponds to the probability of an event. So we now can set aside tails of this distribution such that the probability on the left is, let's say, 0.05 divided by 2, to the right 0.05 divided by 2, so that the probability of observing something in the red region is as small as we would like to prescribe, say 5%. So this is what would happen if in reality there is no difference between the groups. So now what we will do, we'll actually calculate the signal-to-noise ratio from our data and overlay it on top of this distribution. And so if it falls inside this white region, then we'll say, yeah, well, that's what we expected. So there is no evidence against anything that we assumed. However, if we overlay this quantity on top and it's either in this red region or in this red region, we say, wait a minute, it's unusual. There's very little probability that it will happen if, in fact, the null hypothesis is true. So if, in fact, there is no difference between the groups. So assuming that the independence and so on holds, so then the most obvious thing that will go wrong is that our assumption of no difference is not correct. And so then it is evidence against null hypothesis, and so we reject the null hypothesis. So meaning that there's evidence that one group is systematically larger or smaller than the random variation. And so that's really what we do. So this alpha is set or defined before collecting the data, right, before doing the experiment, and this is our decision rule. Alternatively, we can describe exactly the same type of decision using p-values. And so p-value would be literally overlaying our signal-to-noise quantity on top of the graph. Because the distribution is symmetric and because the change can occur in either direction, we also put kind of the symmetric counterpart, so we put it on both ends. And now we calculate the area under the curve to the left of the observed value or its symmetric counterpart. And so the areas outside of the observed values, this is a p-value. And so if the area outside of the observed value is smaller than the red area, it's essentially equivalent to rejecting the null hypothesis. And so on one hand, we can make these decisions based on the rejection region. On the other hand, we can make these decisions based on the p-values. And so the p-values are kind of easy to handle in the sense that they're all on the same scale, right? So we can set a cutoff in advance. And if we have a very large number of proteins, it's very easy to report and summarize. However, they have many drawbacks. And the first drawback is that it loses the information on in which direction the change occurs. It also loses the information about the magnitude of the change. So if it's a small change or a large change, we can end up with similar looking p-values. And so a better way of reporting the results, especially if we have a small number of proteins, is providing interval estimates. And so we talked about two types of intervals, right? So it's the difference plus minus, or individual groups plus minus standard deviation, mean of the group plus minus standard error, or confidence interval, right? And so standard deviation tells us how much variation we have in the data. Standard error tells us how much confidence we have in the mean of the data. So it's a different concept, right? Confidence interval tells us if all the assumptions that we make verify, this is the probability with which the interval contains the true value in the population. So if all the assumptions verify, if we use this procedure to construct confidence interval, let's say 95% confidence interval, and then 95 intervals out of 100, if we collect the data 100 times, build a confidence interval for each data set, then 95 data sets out of 100, the interval will contain the true value. So it has the probabilistic characterization of how likely we are to contain the true mean. So the mean of the data plus minus standard deviation or mean of the data plus minus standard error do not have any probabilistic characterization, right? So it's really confidence interval. And we build it using the same student distribution that we used for testing the hypothesis, and it really is just another kind of version of the signal-to-noise ratio, right? So this is our signal, this is our noise, and this multiplier is this value in the student distribution. Okay, so that's what we agreed, right? And then we talked about different representations of confidence intervals, right? So, or error bars in general. And so we talked about the fact that it's important to document which error bars we're showing, and different error bars will be useful for different message that you want to convey, right? Okay, and then an important concept which will be very important for us today is statistical power. So what we did so far for hypothesis testing, we assumed that there is no difference between the groups. And we say, okay, let's see how consistent this is with our data. But really, in most cases, we do these experiments because we're interested in the alternative, right? So we want to know if there's a difference, and if there is one, we want to find it. And so the concept of statistical power is related to that. So if the null hypothesis is true, we will use this distribution as our reference. Let's say we put all the alpha on one tail. It's possible, right? So we don't have to put it on both tails. So this is our rejection rule. However, if, for example, the first group, the protein in the first group is upregulated, then the signal-to-noise ratio will systematically deviate from 0 towards larger positive values, right? Because group 1 has larger abundance than group 2. And so if, in fact, the alternative was true, so if, in fact, there was a difference between the groups, the same signal-to-noise will actually, the distribution of it will be shifted towards positive values. But our decision is based on that because this is not known, right? So our decision is based on that. So the probability of our signal-to-noise exceeding this threshold is actually larger if the alternative is true. And so this blue area here is the statistical power, right? So the pink area here is sometimes referred to as false positive rate or type 1 error. The blue area here is the statistical power. So what is the probability of finding a difference if, in fact, the difference exists? So this is what we want to do. And so now, like as we will later today talk about sample size calculation, we want to know what we will do in terms of type 1 error, but we also want to know what will be our power, right? So what is the probability of finding the difference given our experimental setup? So this will be really our main consideration. Okay, and so we also talked about the fact that kind of a naive way of increasing the power is increased type 1 error, right? So if we allow more error, if the null hypothesis is true, of course we will find more differences, right? But we will also make more false positives, so that's not really a good way of doing this. So other ways would be to consider, well, how big the difference is between the groups, right? So if we're interested in changes which are very large, it will be easier to detect them, right? That's quite obvious. But also if our sample size is large, the denominator will be smaller, so signal-to-noise will be larger, right? On the other hand, if the variation in the population is large, it will be more difficult to find changes, right? It will be more difficult to shift the distribution to the right. So these are the considerations that we need to keep in mind. Okay, and then we also said that complex designs can also allow us to essentially gain sensitivity because we bring in more replicates from multiple but related conditions. Okay, and then we spent some time talking about all the problems that p-values have, right? And so the main underlying kind of fact about the p-values is that these are random variables because they're summaries of the data, so we overlay something that we calculated from the data on top of this reference distribution, on top of the student distribution, but it depends on the data, right? So if in a data set the observed signal-to-noise changes, obviously the p-value changes as well, right? Therefore, the data are random, signal-to-noise is random, and therefore the p-value itself is also a random variable. And so just like we do not expect to have exactly the same numeric values in the data when we repeat the experiment, there's absolutely no reason to expect exactly the same p-value when we repeat the experiment. So this is also subject to randomness. And so we talked about like misconceptions that people have in terms of p-values. And then we talked about the fact that the distribution of p-values, if we repeat the same experiment many, many times, depends on the sample size. It also depends on the difference between the groups and so on. And so the danger of that was that if we have an experiment with small number of replicates, first, we're unlikely to find many things, and second, when we find something, we tend to grossly overestimate the magnitude of regulation. So there are really many kind of issues with that. Okay, and so this is where we left off last time. So we essentially started talking about the fact that in the experiments that we deal with, we never, or very rarely, study one protein at a time. And in fact, much of research now goes into multiplexing our experiments and being able to quantify as many analytes as possible at once, because this is effective, right? And the hope is that we can learn more underlying biology if we quantify more analytes simultaneously. But the danger of that is that by looking at more things, we are more likely to uncover artifacts. And essentially, we need to be more careful with the statistical analysis when we work with multiple analytes and not just with one analyte. And so this is something we need to do. And in fact, when this type of methods came about in biology, so with the advent of microarrays, somewhat over 20 plus years ago, it really actually generated a lot of motivation for the development of new statistical methods, which really work in high-dimensional spaces, and it really allowed statisticians to do work which was not really needed in a way prior to that. So the corrections for multiple testing is definitely one of these cases, which was motivated by gene expression microarrays at that time. So we just started that, talking about the fact that we have, like in this particular example, an fMRI, right? So if we look at enough brain regions in dead fish, just by making enough hypothesis tests, we will find some which have small p-values, right? Or some which are in the rejection region by definition, right? Because we say we have a proportion of false positives 5%. So if we make 100 tests, we will find 5 things which will be false positives just by the definition of the procedure. And of course, these days we have more than 100 proteins, so it inflates the number of false positives that we may have. So we need to deal with that, right? And so we kind of try to look at the Shiny app, which essentially shows how easy it is to get false positives when we make enough hypothesis tests. Okay, so let's now look at this a little bit from more kind of technical perspective and see exactly what we can do about that. So I'll have a hypothetical example where we only have 2 proteins. And so now I have simultaneous test of hypothesis for protein 1 and protein 2. So now I'm plotting the student distributions. I kind of flip it here for protein 1, and I have another student distribution for protein 2. And so for each of the proteins, I calculate separately this signal-to-noise ratio, right? And I want to make a decision. So for example, for protein 1, my alpha over 2 here and alpha over 2 here, this is my rejection region. So if for protein 1 the null hypothesis is true, then I would reject it if my signal-to-noise ratio is here or here. And I will do it regardless of what happens for protein 2. So in fact, my rejection region is this area here. Because for protein 2, no matter what happens with protein 2, this is what I do for protein 1. And so this area, because this is a probability distribution, so the area of this rectangle plus area of this rectangle is, let's say, 5%. But now I do the same thing for protein 2. So this is my rejection region for protein 2. And so if protein 2 is in this region or in this region, regardless of protein 1, I will also reject the null hypothesis. Right? But the fact is that my experiment has both proteins and not just one or the other. So what I'm actually doing is this, right? So I'm rejecting the null hypothesis for one or for the other. And now my probability of making at least one mistake in at least one of the 2 proteins is the combined area of both rectangles, which is of course more than just the one protein or the other protein. So my probability of making at least one false positive mistake increased. And you can probably easily imagine that if we now do it more and more proteins, so essentially the probability of making at least one mistake, right, of at least one false positive is pretty much 1, right? Because very quickly this probability will be increased. And therefore, if we're interested in the whole collection of experiments, what we have done so far doesn't work anymore. Because if we control the proportion of false positive for one protein, we do not control it for the whole family of experiments, for the whole collection of experiments. So a way to do this is essentially be more conservative, right? So now, if instead of making my decision boundary outside of these red lines, I push my decision boundary for each of the protein kind of back, right, towards more extreme values, I can do it in a way that the combined area outside of the dashed line is what I want, let's say 5%. And it is possible, and so in fact a lot of the kind of research goes into how can we exactly define this dashed line, right? How we define this boundary. Because you see that for each individual protein now the dashed line goes more and more into tails, meaning that we need to have more and more extreme values of signal-to-noise ratio to claim that we reject the null hypothesis. So it becomes more and more difficult to reject the null hypothesis in this case. And so how can we do it? And so as I mentioned, there's a lot of statistical research that went into this in the last years. And essentially there are at least three considerations we can kind of think of that how people went from one protein to many proteins. And so one is, what is the multivariate version of the error rate? So we just said type 1 error is reject the null hypothesis when in fact it is true. But when we have many proteins, what does it mean? Is it a good thing to say, I want to control the probability that I make at least one false positive, or maybe I can have some false positives, maybe just not too many. So this is something which we can consider. The other is, how do we define the null hypothesis with many proteins? Do we say that all of these proteins simultaneously do not have a change, or maybe there is something else? And then also, how do we define this multivariate distribution? So do we still talk about multiple student distributions? Or maybe, so essentially having some rectangle like that, or maybe there are some kind of associations between the student distributions. So this is, and you know, we don't have time obviously to go through all of these methods, but just so you know, different methods, they really differ in how they answer these three questions. And as always, right, the more complicated method we have, there are more complicated ways for the method to fail, right? So some methods will be simple, but they will be more robust. Maybe they don't have as much sensitivity. Others will be more complex, but they can also fail in many ways which we may not even understand. So that's really the idea behind them. So let me just give you a very kind of brief overview, and I will just highlight a couple of things which are very popular, especially in high-dimensional biological data, and in particular for mass spectrometry proteomics. So this is a typical way to represent the situation that happens if we have more than one protein. So we have, let's say we have m proteins total. So here is the truth. So these are true proteins which do not change, and these are true proteins that change. The problem is we don't know which is which, right, and how many, because we do not observe them. But this is the truth, which we assume exists out there. And so this is our decision. So this is the proteins which we claim are not changing, according to whatever decision rule we want to make, right? And this is the proteins which we claim are changing. So what we actually observe is this R. So R is the number of proteins that change. And of course we observe the total number of proteins, M. Every other quantity is actually not observable. But we assume that it exists, right? And because our decision is based on random data, so the quantities in this table, they're also random, right? So R is random, V is random, so M and M0, they are fixed, because we assume that in the population some proteins change, some proteins don't change. But our decision based on random data, therefore the quantities in the table are also random. And so what we've done so far, when we talked about student tests, so alpha, which was set aside in the tail of one distribution, it is actually the probability of type 1 error. So if we take the same protein over and over, make hypothesis tests, and in fact the protein doesn't change, then alpha % of time we will find a change by random chance. So this can be formalized as the V divided by M0. So out of all the proteins that do not change, what is the proportion that we actually find changing? And E here stands for expected value, meaning that if you do this many, many times over, so this will be the average of these many repetitions. So this is the probability of type 1 error. Now this will be for one protein. However, what we just talked about before, how can we control the probability of making at least one false positive in the entire family of experiments? So you probably have heard about a correction for multiple testing by Bonferroni, where we take alpha and divide by number of experiments. That's exactly what it's doing. So Bonferroni correction says, okay, I want to make sure that the probability of making at least one false positive is as small as I would like. So in the terms of this table, this is said, well, I want essentially V to be 0. I want V to be anything but 0 with a very small probability, say 5%. And so what Bonferroni would do is take alpha, divide by the number of experiments, right? And this has been a state of the art until, let's say, microarrays came about, because for statisticians at that time, many tests would be like 20, right? Because the technologies were not available, computational tools were not available. And then microarrays came along, and we have like a lot more, right? And so now we realize that if I take alpha 0.05, and I have 1,000 genes, right, and divide this by 1,000, then I have to have really, really, really strong evidence to avoid having false positives. Because, the best way to avoid false positives is to not find anything, right? Then we're sure that we don't make any false positives. But that's not really why we're doing the experiment, right? So essentially, very quickly, this became unsatisfactory for this type of research. And so then, I remember I was saying there are different considerations. So they essentially multivariate type I error, right, and so on. And this is the research by two scientists, Benjamini and Hogberg, who essentially proposed something else. They said, okay, instead of trying to control this family-wise error rate using things such as this and pushing the decision boundary into extremes and requiring some strong evidence for change, let's change our criteria. Instead of saying we want to control the family-wise error rate and keeping V 0 with very high probability, let's say we can have some false positives, because when we compare, several thousand proteins, it's okay if few of them are false positives, right? As long as we can control the proportion of false positives in our conclusions. And so essentially what happened is that they proposed to change their criteria, and instead of looking at the family-wise error rate, keeping V close to 0, they said, okay, we want to control the ratio of V to R. We want to control the proportion of false positives in the list of claim changes. And again, this is just a technicality. You don't want to divide by 0, so you say, okay, maximum between. In our case, we always find something, so this is not really very important. And again, V is a random variable that is not observable. R is observable, but again, Benjamin and Hogberg, they came up with essentially a set of assumptions and an approach which allows us to control this proportion of false positives on average. So again, you have this expected value in front. So if we keep collecting the data and repeating this procedure many, many times, we can claim that on average, the proportion of false positives would be whatever we want it to be, 5%, 10%, and so on, which we also set up in advance. Let me take a break for a second. Does it make sense? Okay. So we need to work harder, essentially, when we look at larger spaces of proteins. And the way to deal with this statistically is, on one hand, to understand what does it mean in this multivariate space to reject null hypothesis, but another say, well, what do we actually want to ensure? And so it turns out that family-wise error rate in Bonferroni is just too strict when we have too many proteins, and we can live with some proportion of false positives if we can control what this proportion is. And so now different kind of methods work off that. And let me just give you a preview. This is the type of reports that you would see. So if you stay for the next week, this is, for example, what MSStats is doing, but it's not just MSStats. It's very standard now in this field. So if we have multiple proteins, each dot is a protein. So for each protein, we will report the log fold change. So this is what we call a practical significance, right? So how big is the magnitude of change? And the y-axis is p-value, but it's adjusted to control for false discovery rate. And it's also on the minus log scale, such that large values means large statistical significance. And so now the horizontal cutoff will control false discovery rate, and the vertical cutoffs can be an extra cutoffs to also have a fold change filter. And so that's what we'll talk about. So the next few slides talk about how we get to this y-axis. Okay. All right, so let's talk about Bonferroni first. I think just because it's simpler to think about. So just as in the case of one protein, if we have an experiment with many proteins, we need to decide what would be the family-wise error rate. So what is the probability of V being anything but 0? We want to set it in advance. So then, if we work with the decision rule, we have M p-values. So we have M proteins, right? So for each protein, we have an M p-value. So from each protein, essentially testing the null hypothesis. And we compare each p-value to alpha divided by the number of proteins, right? So if alpha is 0.05 and we have 100 proteins, now we compare each p-value to 0.005. And if it's less, then we reject the null hypothesis, right? What we can also do, remember, so this is based on the decision rule, right? So we have the rejection region. Turns out we can actually replace this with a similar type of decision. So if I compare my p-value to alpha divided by M proteins, it is essentially the same as comparing M times P to alpha, right? It's the same conclusion. Well, now M times, so p-value is between 0 and 1, like it's a probability. Now M times P can be anything, right? So we can say it as the minimum between M times P and 1, right? So essentially to truncate it to 1. So this quantity is called an adjusted p-value. So now the p-value, adjusted p-value, is adjusted for the fact that we have M proteins all together. And so now if I take adjusted p-value, I can compare it to my original 0.05. Right, so same idea, but now I don't have to think, okay, I have alpha 0.05, but I also have that many proteins, now I need to change it. So just adjust the p-value, and from this point on, the cutoff of adjusted p-value controls family-wise error. And so if I wanted to make a volcano plot, so my adjusted p-value here would be exactly that, right? I just multiply this by the number of comparisons. And so these are two equivalent ways of making decisions, right? So either you compare p-value to this, or you multiply by m. Okay. So but as we said, this is too conservative because it really wants to V be anything but 0 with very small probability. And so the really seminal work by Benjamin and Hochberg was not only to say, let's change the criteria. Instead of having V being 0, let's have some proportion of false positives. But they also came up with a kind of procedure similar to this, which allows us to actually control the average proportion of false positives, even though V is not observable. And so what they did, so this is the algorithm, and it's again based on the decision or based on the adjusted p-value. So let's look at the decision rule first. So we have M proteins, right? So we have M p-values. So all I'm doing is sorting the proteins by p-value. This is the largest p-value, so least significant, right? And this is the smallest p-value, most significant. And so now I'm working my way from the least significant to the most significant. So here, and by the way, just like with the Bonferroni, we set alpha family-wise error rate, let's say to 5%. So let's say false discovery rate. Let's say false discovery rate is 5% as well, right? And so this false discovery rate, just traditionally from this work and related work, is denoted as Q. So see, I put alpha star here to indicate family-wise error rate. So now I set false discovery rate to some value Q. Let's say 5%, right? So we want to have 5% of false positives in the list. So now I take the largest p-value in my data set, the least significant, and I compare this to this cutoff times m divided by m, so essentially 1, right? So I compare my least significant p-value to 0.05. If it's larger, I say, okay, cannot reject the null hypothesis, keep going. For the next time, now I reduce the nominator. So now I compare this to m minus 1 divided by m times q. The next will be m minus 2 divided by m. The next will be m minus 3 divided by m, and so on. And the first time I find one where my p-value is less than this compared value, then I claim significance, and I say that the remaining list of proteins, they're all significant, essentially to make it a monotonic decision. So essentially what happens is that at the lowest end, I compare this to the cutoff without any adjustment. At the end, with the most significant proteins, it's identical to Bonferroni, where I divided by the number of proteins. But in between, these values kind of have an intermediate procedure, right? So it's not quite no adjustment, but not as strong adjustment as with Bonferroni. And because the cutoffs are not as strict, it allows me to be more sensitive. So I may be able to claim significance for that, but I may not be able to claim significance for 1/n. And the value of this work was really twofold. So one was changing the criteria, and the second is showing that this algorithm actually works. And it controls, on average, the proportion of false positives in the collection of proteins. And so we can do that, and actually many people do that, but kind of in that spirit, we want to also be able to not worry about, okay, what's my cutoff for this particular protein and do these calculations all the time. We want to transform the p-values themselves so that we can only remember the false discovery rates that we want to control, right? And so now what we'll do is the same thing, right? So just as before, I'm multiplying p by m. So now in this case, I have essentially, so now instead of alpha, I have q. Right? I have n minus k here. So what I can do now, I can take my p-value, multiply by m, divide by m minus k, right? Compare this to q. And then there's a little bit more of, well, first of all, make sure that it's still a p-value, right? So taking the minimum of this and 1, so that if it exceeds 1, we just truncate this to 1. And then there's a little bit more, so taking essentially the lowest, the highest value of the p-value here, just to ensure that this is a monotonic transformation. So essentially, well, you can even ignore this for the moment. So just like in Bonferroni, we multiply the p-values by these constants such that the result can now be compared to q. So I think I have a typo. I don't have k minus 1. No, it's k. Sorry. So it's working from the top to the bottom. So essentially the same idea that we don't want to remember what is the cutoff for each protein depending on the order of the protein in this list. So instead we multiply the p-values by this constant. So now that this on the transform scale, the p-value can be compared directly to the false discovery rate cutoff, right? And so this false discovery rate is traditionally denoted by Q. And so now, if we think of the largest error rate, so if I draw the distribution just to make sure, right? So if this is for a single, so this is my t, right? So this is 0, this is minus t. So if on the adjusted scale, this is the smallest error rate at which we reject the null hypothesis while controlling false discovery rate at q. This is called the q value. So essentially, q value is the counterpart of the p value when the p value are adjusted to control for false discovery rate. And in kind of statistical literature, q values, the term q value is not used very much. So it was kind of used once in a particular publication. Turned out that this publication was very influential for mass spectrometry and proteomics. And so if you think about, for example, LCMS and database search, everything is presented in terms of q value. So q value essentially is a p-value cutoff when the p-value is adjusted for multiple testing. Well, actually, that is a difference because Bonferroni, remember, if I go back here, Bonferroni doesn't control false discovery rate. Bonferroni controls family-wise error rate. Therefore, you would not refer to Bonferroni's Q-value. On the other hand, if you control false discovery rate with different methods, such as Benjamin-Hochberg or Story method or Efron's method or others, they will all be controlling the same quantity, and therefore they all have Q. Exactly. And if you talk to statisticians, they would probably have to think a little bit before remembering what Q-value is, because it's just not as much used in that literature, but in the mass spectrometry and proteomic literature, it is a very kind of common notation. So let me take a pause here. Does it sound okay? Right. So let's see once again. Right. So we essentially order the proteins from least significant to most significant, and essentially the threshold now is adaptive. So for each protein, we compare it to a different threshold. And so on one end, it's as if there's no adjustment. On the other hand, as if it was Bonferroni. The first time we claim significance, the remaining of the list is significant just to ensure monotonicity. And we can do this from the decision rule perspective, or what we can do is to multiply the proteins by the inverse of that, truncate it to 1, have this extra rule to ensure monotonicity of our decisions. And so now these adjusted p-values we can compare to the false discovery rate. And this will ensure that we control the false discovery rate. And so if I go back to this plot, this is exactly what it is. And so in particular, when you will see next week MS stats is returning this, it returns exactly this quantity. Okay, so this is for Benjamin and Hochberg. So the problem with this, so remember I talked about different considerations, right? So Bonferroni, Benjamin and Hochberg, and other methods, they all essentially assume the worst case scenario. What happens if, in fact, all the null hypotheses are true? So if all the proteins are not changing at all, this is the worst case that can happen, right? So this will be the proportion of false positives that we will find in this particular kind of workflow. Now, oftentimes we do experiments because we hope that not everything is not changing, right? So we hope that there are some changes in the system. And if there are true changes, well, they cannot produce false positives, right? So false positives can only be produced when there is no change. And so quite a bit of research went into the kind of understanding, okay, how can we first guess what is this value of M0? So that we can exclude from consideration the number of proteins that are truly changing and only focus on the proteins which can lead to false positives. And so one of such approaches was by John Story. And this was at the time when he was at University of Washington, and he was working very closely with Bill Noble and Mike McCoss, and so this work was very influential for some of the mass spectrometry work. So this is what John Story proposed, and there are multiple versions of this, but I'll just give you one. And by the way, this comes from this reference. I put it here because it is from Journal of Proteome Research, so they try to describe false discovery rates in the language of mass spectrometry and proteomics. It can be quite useful. So what I haven't had a chance to tell you yet is that when we have many null hypotheses, and we do hypothesis testing, generate p-values, and if all the null hypotheses are actually true, so there's no change anywhere, the probability, the p-values are random variables, and they have a probability distribution. So this probability distribution is uniform. And this can be shown mathematically as well. So if you now calculate p-values from the entire experiment, and you know that a small number of proteins are changing, others are not changing, you make the histogram of p-values. If all the assumptions verify, it will actually look like that. So you will have a whole bunch of p-values that form a uniform distribution, and they have some p-values which are very small, so those correspond to truly changing proteins. And so what John Story proposed is to say, well, let us first figure out what is the proportion of truly changing proteins. So we can take the part of the data which clearly follows the uniform distribution, fit a uniform distribution to this. This will tell us what is the proportion of proteins that do not change. And then he showed that a similar kind of algorithm will control the proportion of false positives by essentially looking at the number of false positives here divided by the combined red and green region here. So essentially, if I go back to the definition, we want to know the proportion of V over R, right, on average. So how many false positives in the rejection region, right? So Now, this will be my decision rule, right? So these are small p-values. I will claim that they're significant, right? These are large p-values. I will claim they're not significant. And so now the proportion of false positives will be the number of, the estimated number of proteins in red rectangle to the total number of proteins in the rejection region. And they can estimate this number in red rectangle by fitting a uniform distribution. So essentially they see, okay, what is the height of this distribution which matches the height of the distribution of p-values in large values. So essentially it is nice because now it can use the fact that a large proportion or some proportion of proteins is changing, therefore they cannot give us false positives. So they estimate this M0 from that. The problem is that it requires an additional curve fitting, right? So we want to fit a uniform distribution to this. So this is a nice case, right? Kind of idealized case. What if we have p-values which are distributed, I don't know. And this is a very common situation. So where do we fit the uniform distribution? Do we fit it here? Do we fit it here? Do we fit it here? So they have some technology behind this based on resampling, which kind of finds an optimal point. But effectively, now we make more intense use of the data, and since the data are random, our decisions are also subject to random variation, and therefore this method tends to be less numerically stable, especially in situations when we have many things potentially changing, or we have a lot of random variation, or we have some batch effects, or some potential violations from independence, and so on. So in our group, our personal choice is go with this, because it may be less sensitive, but it's more numerically stable. And so we think that this kind of gives us more reproducible results. But for example, in database searches in LCMS, where we have large numbers of MSMS spectra and people want to kind of gain sensitivity, so there's more curve fitting going on to this type of distributions. So these are choices, and as I say, they trade off kind of advantages and disadvantages. So these methods will be more sensitive, they will be less numerically stable. This method is more numerically stable and more reproducible, but it's less sensitive because it assumes the worst case that everything is changing. But something has to be done, right? Oh, sorry. Actually, it is kind of like that. It's kind of exactly like that for this particular method. So what you can do, even in this example, right, you can say, okay, I can fit, I don't know exactly what's going here. So let me take just half of the data and fit uniform distribution on this. So essentially get the height of this distribution from half of the data, right? Or let me take 2/3 of the data, right, and get the height. In this particular case, it wouldn't matter because it's an idealized case. Very nice, right? But then you start getting into this region, right, and then it may affect the height, right? And so when you have things which are not very clear-cut, so then it really make a difference in terms of your estimate of false discovery rate, because the height of this uniform distribution is not as clearly defined. So in this particular case, there will be no problem, but in many realistic cases, it may be an issue. Okay, so that's. Let me take another pose. Yes, please. For anything, of course, because this actually does not depend on the data collection, right? The only thing it depends on is the statistical assumptions, such as independence, right, deviations from normal distributions, and so on. So as long as your p-values are correct, this will work. And the p-values are correct if they are derived from the assumptions that match your experiment. So for example, so the independence assumption is really crucial, right? But if you did not randomize, right, and you have some kind of day effects going on, or some kind of batch effects, or plate effects, or something else, right? So this can really give you p-values which are very different from what they should have been. Then this can have all kinds of complications. But here's another thing. So these methods, everything I've talked about so far, also assume that different proteins are independent from each other. And that biologically is much more tricky, right? Because, right, things work together, right, biologically. And so another method, which I don't have here, That's the method by Brad Efron, which works specifically on relaxing the assumption of analytes being independent. But it requires more curve fitting, so I kind of skip that. So every time you make it more flexible, right, and kind of trying to gain sensitivity and reflect real assumptions, it requires more complicated models which lose stability. So I show this because I know that this is really influential for mass spectrometry, right? This is what I would do for quantitative studies, right, specifically for multiple testing. So Efron's method would transform p-values on the scale of normal distribution, and it's kind of, if you're familiar, for example, with LCMS, with peptide profit, and so that's kind of similar type of method, fitting the curves. Well, so, no, that is what you get to obtain adjusted p-value, right? So essentially, then you would, so you fit this curve, right? And then you, for any, yeah, actually I didn't say that. So you fit this curve, right? And so now if you know what is the proportion of proteins that are not changing, for any different vertical cutoff, you can calculate this quantity, right? And so then so the way it actually works, you just vary this alpha, right? For each alpha, you calculate this quantity, and then you find alpha, which gives you the quantity 0.05 or something like that, right? And this is your decision rule. And if you have the decision rule, then you can get the adjusted p-value from that. Okay. All right, so that's what we do. And so here is just, I put it here also from the points of significance series. They speak more about that and compare different methods. Here is what happens when only 10% of proteins are changing. Here is 50% of protein changing. So this is false discovery rate or false positive rate. This is a power. And essentially the conclusion is, and you can look at this maybe on your own from the vignette, essentially, if you don't adjust at all for multiple testing, you have a lot of sensitivity, but you have a tremendous amount of false positives. If Bonferroni will have no false positives, but it will have no sensitivity, right? And so essentially false discovery rate controls that kind of in between, and that's what we want, right? So that's the idea. Okay, so now, this is a topic which is actually very close to my heart, because statisticians, and I'm trained as a statistician, right? And we spend a lot of time talking about what we just discussed, right? Different mathematical constructs, right? Different probability distributions, assumptions, and summaries, you know, and so on. What all this math ignores is the fact of how the data came about in the first place. So how the question was framed, how we decided to set decision rules, how various aspects of the data were included or excluded from the study. And in my opinion, you know, the math we can learn and we can implement and we can have software, we can do it, right? But this kind of informal aspects of data collection, of experiment, of kind of conducting the experiment, actually crucial for reproducibility, right, and for success of our studies. And I'll just give you a little bit of examples. So, and it's actually conversations I have very often, and in fact I even had this type of conversation this week. So this is another just a commentary from Nature, which talks about all the steps which go into getting essentially our conclusions, right? And so we design the experiment, we process the samples, we collect mass spectra, we process the signals in mass spectra, we have some model, right? We have a signal-to-noise ratio, we have a p-value, we adjust for multiple testing, right? And then we don't like what we see. So our favorite protein is not changing, right, or something. And it happens so often that people say, you know what, this adjustment for multiple testing really doesn't work for me. So if I just don't adjust, is it okay? Right? And then they will say, I have such a small sample size. So, you know, maybe in my case, because I have very small sample size, can I not adjust for multiple testing, right? And so what we're saying is, wait a minute, you did all of that, right? And it doesn't work, and you blame multiple testing, right? So it doesn't work that way, right? And so this is something which is really important for us to understand, that all of that, right, that went into this adjusted p-values really matters. And it has to be a really important part of the experiment. I'll just give you some kind of highlights. So this was one also from the blog by Jeff Leake. So there's so many examples I just kind of randomly take. So this was an antidepressant Paxil was studied for several main outcomes. and none of them showed an effect. But while doing that, they also measured some other things because they could as part of the study. So they said, oh, wait a minute, but that particular endpoint seems like it is affected by the medication. Let's go ahead and market the drug for that particular endpoint. So the study was not designed for that. The study was designed for something else. And along the way, they found some associations with some other things. Oh, let's change our conclusion and let's say that this drug is actually good for some other thing. Well, if you collect enough measurements, some of these measurements will be apparently affected by the drug, but you cannot claim with confidence that the drug really is affecting this because the study was not designed for that. And indeed turned out, so they switched the outcome, they marketed the drug, turned out it was not reproducible because it was an artifact of looking at long enough at enough things to find some. So this is one, right? So this is another, and this is Andrew Gelman. He's also a big advocate for reproducible research. So essentially, again, it's an issue of data selection and analysis protocol not specified in advance. So this was a study of two groups, women at peak and off-peak fertility cycle. And well, arguably this is not an easy thing to determine, so they kept changing. Okay, so the previous was changing the endpoint. Here they kept changing which woman is in which group. So is it peak or off-peak? And so they kept moving women between the groups, right? And so what they found that at peak fertility, women are more likely to wear red or pink shorts. You know, you can find things like that, right? And again, I trust that all the math was right, and they did the p-values right and so on. But this really is an important part of the protocol, which I know that in clinical trials and studies like that, this is very well known, very well understood. Somehow in kind of high throughput technologies, when these are new technologies measuring many things, people think that it doesn't matter anymore. It very much matters. It is really important. So these are more important parts which can affect the p-values we don't like than, you know, just the adjustments for multiple testing. Okay, and so this is just one. I put a link here for you. Let's see if I can find. So there are many examples of this. So this is 538. I don't know if you're familiar with this. So this is a kind of data-driven journalism, right? So these are researchers or journalists, I guess, who try to make kind of points in social commentaries and so on based on data. So in this link, you will see they have data on different type of performance of economy based on employment, inflation, GDP, stock prices, and so on. And they measure, so they have records of who was president, who governors, senators, and so on. And so essentially, the goal is to show that Republicans are better for economy or Democrats are better for economy, right? And essentially the point here is that you can pick anybody, right? And if you click at enough kind of things that you include in your study, do you want to look at presidents? Sorry, I don't know how to use this computer. Well, try it on your own. So if you select enough inputs in your data, so do I want to only look at presidents or presidents and governors and senators and representatives? Do I want to measure economy by GDP or by inflation or by employment? You can make your point. If you think Republicans are better, you will make your point at p-value 0.05. If you think Democrats are better, you can make the same point, right? So by just playing enough with the data and including and excluding things. So same thing, right? So the message here really is that the protocol for all the steps of data collection and data analysis has to be specified in advance. And this includes type I error. This includes, you know, false discovery rate adjustments, and this includes other things. So it is a really important point. And this is just kind of to finish that. So this is an article, which year was it? 2011, but it's still quite relevant. Journal of Psychological Science. Undisclosed flexibility in data collection and analysis allows presenting anything as significant, right? And for us, it really matters, especially because we have such high-dimensional data sets. So it's really easy to find artifacts of the protocols, and SOPs are not specific. Okay, and that's what we want to do, right? So we want to get away from this, and we want to get to this. Okay, so this was actually the end of my yesterday's talk. So now we can move on to our today's topic, but maybe before that, let me take another pause and see if you have any questions.
Is there a rule of thumb in terms of how many like the ratio.
Hold that thought. Yeah. Any other questions? Well, okay, since that's a question, let's just go into that. And I hope you can hold all the information. And if not, it's recorded, right? And the slides are posted, so make sure you come back to that. Okay, so how many replicates do I need? So this is, if there's one question that my collaborators ask me most often, it's that, right? And as I said earlier, the answer to this is, well, it depends. And this is not the answer that they like usually, right? They say, okay, but I don't know if you have seen this video, but my grant is due tomorrow. Can I use 3 patients? We always use 3 patients. So the short answer is, it depends. The right answer is, okay, let's take a look more closely, right, at the information that we have. Because fundamentally, designing the experiment is like predicting future. We're trying to project what our future experiment would look like, and we want to make sure it has properties that we need, right? But prediction is hard, especially about future, so we need to have some data to kind of inform us about that. So let's just review from the beginning, right? So one of the important principles is replication. So replication allowed us to carry out the inference in the sense that here we have exactly the same difference between the groups. In this case, all the subjects have protein abundances tightly clustered around the mean, so this is likely a systematic change, meaning that probably we will not need as many replicas to detect this change. This is exactly the same fold change, but large variation around the mean, and so then it probably means that we need to have a lot of replicas to be really, really confident in this mean, really, really confident in this mean, to claim that the change is systematic, right? So the sample size will depend on one hand on the fold change, and on the other hand on the variability that we have between the samples. And by the way, as we said earlier, because we have 2 layers of variation, the biological variation and technical variation, we will have 2 types of replicates, right? Biological and technical replicates. So we'll see how far we get, but I'll just show you how essentially statisticians think about these problems. So this is what we do. We've seen this already, right? So we start off with the signal-to-noise ratio, and we want to make sure, in terms of the performance of the future experiment, we will set up type 1 error. Usually type 1 error is really very cultural, right? Depends on different fields, but somewhere between 1% and 5% and 10%. So these are kind of typical values. And so what we really want to know is what would be the statistical power if we fix in advance the type 1 error. And as we said before, so the true difference between the groups, the variability and the sample size will determine how much power we'll have. So how much to the right the distribution will be shifted if the alternative is true. Okay, so in other words, we need to know quite a bit about our experiment to actually calculate the power, right? And so the way it works, and again, there's math behind this, it's not a complicated math, but we can show that if we fix alpha, so this is a probability of false positives, right? So this is the area under the curve if the null hypothesis is true. If we fix beta, which is the probability of a true positive discovery, right? So the probability of finding the difference if, in fact, it is true. Oh, I see that they use a different notation, so let's call it beta here as well. I just took it from the vignette. Delta is the anticipated fold change. So delta is the difference between the means in the underlying population. Now, this is tricky, right? Because what do we know, right? We don't know exactly what the difference would be. But again, this is something we can kind of assume. And in fact, we can assume the lowest fold change, which would be of interest to us. Because if we can detect that, clearly we can detect larger fold change, right? So we really need to kind of assume the lower bound, which will be of interest to us. Higher fold changes will be easier to find. And this is, by the way, log fold change, I should say. Because remember, we speak in terms of log changes. So if we have, so those things are not difficult, right? So power, we can kind of see what we would like. Alpha is kind of from the kind of research culture, right? Anticipated extent of regulation, we can also kind of figure out. What is difficult is to know how much biological and how much technological variation we have in our experiments. And so these 2 numbers, this is where the pilot studies can really be helpful, because this depends on the biological system, on the type of proteins we measure, and also on the measurement technology. So clearly, if you measure something with DDA, it will be very different technological variation than if you do SRM, right? Or if you do DIE, for example, TMT, anything, right? So clearly, this measurement technology will determine quite a bit in terms of the technical error. And so then mathematically, we can say that, remember in the very beginning, I was saying that the power is determined by the variance of that, so it's essentially the denominator, right, in the square root of denominator in the signal-to-noise ratio. So essentially, if these are the quantities which we want to fix, then the variance controlled by this quantity will control the power at the desired level. So let me unpack this a little bit. So essentially what we want is to make the variance of this difference as small as possible. So delta is the anticipated fold change, right? Log fold change. So the smaller the difference we want to find, the smaller the variance will have to be. These two terms, these are the quantiles of the normal distribution. So I can control that. So if, let's say, if I have alpha here, so this is 1 minus alpha. So this is 0, right? This is the normal distribution, 0, 1. So this quantity is such that the probability to the right is alpha. The probability to the left is 1 minus alpha. So essentially it's a fixed constant. And the same thing for beta. So if the area to the here is beta, so this will be beta. So essentially these two numbers, they are fixed numbers for a given alpha and given beta, which are known. So what we now need to do is to bound our variance by this quantity, which includes the variance in the data and includes the difference between the groups. For example, if I have two groups in the type of experiment we just discussed, so we just said that our noise, right, associated with the difference between two groups is this, right? So it is the variance in the first group divided by sample size, right? Plus, so variance of the sampling distribution of the mean in the first group plus the variance of the sampling distribution in the second group. So this has to be bound by this quantity, and this will guarantee that we have type 1 error alpha and power beta. So what I would do next, so the very simple kind of way, like back of the envelope calculation, is to say, let's assume that the two groups have the same variability, and I will have the same sample size in the two groups. So this is what I would do. So now, if I assume that both groups have same variation, same sample size, here is my formula for the sample size in one group. But we can do things more complicated. Let's say I can only have 1/3 from one group, 2/3 from another group, and so on, right? And so then you can kind of work out this with different types of replicates. So again, if I look here, so if I have larger difference between the groups, I need smaller sample size. If I have larger variance in each population, I need larger sample size. And the same thing here, if I want to have larger power, I will need larger sample size. And if I want to have smaller type 1 error, I will need to have a larger sample size. And usually what we do, so it's kind of, we can look at that, but it's kind of difficult to look at it in terms of mathematics. So what we do, for example, in MS Stats, and this is a very standard thing in statistics, we just make graphs, right? And so here on the x-axis, I plot the fold change, so it will be 2 to the power delta, for example, if it's a log 2. This is number individuals per group, so this is n. And so we would have curves like that. So if I fix alpha and beta, so if I fix type 1 error, and if I fix the power, then this will give me the curve. So as function of delta, I will have the sample size. How did I make this curve? I actually had a pilot study with some patients from which I could get the estimates of biological and technical variance. And so if I had a different pilot study with different variation, I would have a curve that looks differently. And so, by the way, I can kind of give you a heads up. So in MS Stats, what we currently do is whenever you analyze a data set, we immediately treat it as a pilot study for something else. And so we actually extract variance components from that, and we generate as a kind of byproduct this type of curves so that you can inspire yourself from the current study whenever you would need to design experiments later on. So, well, and it's quite obvious, right, that the smaller the difference, the larger the sample size. And usually you can play with different amounts of error and so on. So this is kind of one very basic thing. Anybody sees any problems with that? Exactly. So you know, this is my just like really simplest just illustration, right? And this is why I write it in this way, right? Just to say we need to bound the variance, and this variance will depend on everything, right? On your design, on your variability, on the sample size. So for any experiment, you write out the formula for the variance, and then you solve for whatever you want to solve. Yeah. But what I had in mind when asked about the problem is that this is done for a single feature, right, and a single protein. And we just spent like half an hour talking about the fact that we have many proteins, right? So we need to actually adapt the procedure to account for how many proteins we have. And so, well, that's the next thing. Turns out that this paper, which I mentioned earlier by Benjamin and Hogberg, which introduced FDR, they did another thing which is very useful for us. They also connected the false discovery rate, so essentially the cutoff of false discovery rate, to the type 1 error. So there is so essentially you can say, well, if I use this adaptive procedure, which compares p-value for each protein to the slightly different cutoffs, right, I can tell you what the average type 1 error would be in this experiment. And so this equation actually comes from this paper. And so now what we can do is to specify all of the things that we have, except instead of type 1 error, we will say this is the false discovery rate that I want to control. And so then what we can do is to essentially transform the cutoff of the false discovery rate. It also requires us an initial guess of M0, so how many proteins will not be changing in our experiment. And from this point we can estimate the average type 1 error, and then we use the same procedure as before. So again, this is what MStats implements. So same thing, so now we can essentially draw graphs with that to see how it looks like. So this was the same pilot study, and so now this has 3 different lines. So the solid line here shows the results if we only had 1 protein in the study. And same thing, right? So smaller differences, we need to kind of have more subjects, right? That's clear. Now, these 2 lines, they correspond to the planned experiment if we have more than 1 protein. But so with this method, it actually requires us to know what M0 would be. And so now these 2 lines correspond to 2 situations. So this line corresponds to a situation where half of the proteins are expected to be changing. And this line corresponds to a situation where only 1% of the proteins will be changing. And so you see that if we have a very small number of proteins changing, it requires a larger sample size. And I hope by now kind of the intuition is clear, is that if only a few proteins changing, we have a lot more opportunity for false positives. And we try to control false positives. Therefore, we need to work harder to protect ourselves against false positives. And work harder in this context means getting more data and having more replicates, right? On the other hand, if almost every protein is changing, well, there are few false positives, everything is a true positive. Whatever we find is good, right? Because they're all true positives. So we do not need to work as hard. And so this is something, I think, which is quite important for proteomics community, because a lot of interest currently is, in experiments which screen as many analytes as possible, right? And everybody's like, oh, my protein list is longer than yours, identified more things, and so on. The price for that is that we need to have a larger sample size. And there's a lot of value in targeted experiments, also from the statistical perspective, where we target analytes which we have good reasons to think are changing. Because in addition to kind of seeing the relevant analytes more directly, we also need to work less hard from the sample size perspective and from the statistical perspective. So this is quite valuable. Okay, so let me pause here. Questions?
obviously in the mass spec it's coupling geometric peptides and we're inferring proteins.
I hope you're staying for the next week because that's the topic of our conversation next week. Exactly. So as I mentioned in the beginning of these 2.5 days, that this is really basic, right? So we're really not very close to the realities of mass spectrometry. But essentially, let me give you an upshot. So the way we advocate to do this is to summarize peptides into proteins first, and then work with summaries kind of along these lines. And the summaries, they're not trivial, and they have all kinds of issues, and we will talk about that later. But that's really what we want to do. Really? Yeah. Yeah. So for the moment, I'm saying let's assume we have a magic technique to get one number per protein per sample, right? On the other hand, and actually this is related, oftentimes people say, you know what, it's not meaningful to summarize proteins. Maybe we have PTMs, maybe we have shared peptides, so why wouldn't we do everything at the peptide level? Which is a valid thing, right? But then we have a lot more peptides than proteins, and then we're back to this problem, right? So the price for this, again, is that we would expand the space of possibilities, a lot more things which are potentially non-changing, a lot more opportunity for false positives. So it may be meaningful, but in this case, if PTMs are really of interest, right, or specific peptides, again, doing things in a more targeted fashion, one way or another, even filtering the results and only focusing on peptides of interest will be very valuable, also from the statistical perspective. Most definitely. So let's talk about this next week if you are staying, but usually, we're just going to give you an upshot. You want to filter features out based on something which is completely orthogonal to the data and comparison. So you do not want to filter features out based on fold changes or anything. That would be terrible, right? Because then you bias yourself towards artifacts, right? But for example, you can say, I'm only interested in phosphopeptides. So you can totally exclude non-phosphopeptides for this study, right? Or you can say, I'm only interested in peaks which I can identify reliably. So even potentially non-identified peaks can be of interest. If I know I cannot follow up on those, you are better off removing them up front because they will, improve your sensitivity for things, kind of like that. And then you can do other things such as, for example, missing value cutoffs and so on. But those are kind of more tricky because you can have systematically missing features in one group. But some kind of really simple things based on IDs, that's very easy. Okay, so let me tell you a few words about things which are kind of more specific to mass spectrometry and relevant to experimental design as well. So remember yesterday I was saying that we can take these models and expand them to more complex designs, right? And so this is kind of what we would do. We'll take, for example, in this particular case, this was a very old study I did like 12 years ago, very, very old, where we were looking at particular protocols in mass spectrometry for the purpose of planning experiments. And we tried to understand what are the important sources of variation. And so in this case, we had a design where we had several, so this is a pilot study, right, in preparation for the real experiment. So we had several subjects included in the study. For each subject, we have sample prep, so we did glycocaptures, a particular type of enrichment, which was kind of experimental at that time. And then for each sample preparation, we did multiple technical acquisitions just on mass spectrometry. And because now we have kind of multiple sources which we can distinguish, right, person-to-person variation, sample prep to sample prep, run-to-run variations, we actually can write a linear model which really describes each point by saying I have a contribution coming from the disease group, a contribution that it comes from a particular person, from particular sample prep, and so on. And we can, and I don't have time to talk about this kind of in great detail, but essentially you can learn the amount of variation from each source. And then you take exactly the same variance, right, that we talked about all along, right, the variance between the two groups, but now our experimental design contains more details. Therefore, I can actually write this variance in the greater detail, and I can say this variance actually has the contribution of biological variation, sample prep variation, and random error variation. And again, this is written just mathematically, you can derive this from this experimental design. And this is a really interesting case because this is an illustration of how statisticians think about which type of replicates are most important. So you see, for example, here, this is the random error, just variation based due to the data acquisition on mass spectrometry. The denominator here is the number of biological replicates, number of sample preps, and number of replicate runs. So you see that if we increase the number of mass spectrometry runs, we will decrease this component of variation. If we increase the number of sample preps, we will decrease this component of variation. But the only principled way to really reduce the variation substantially is to increase the number of biological replicates. So this is kind of how statisticians formalize that, the fact that biological replicates are more important, because this reduces the variation, the noise associated with our signal in the most principled way. And that's kind of more mathematical. So the next thing I wanted to mention also very briefly is blocking, right? So remember I was saying that blocking has also a good property, that not only it enforces the balance, that let's say we have a day effect, like in this example when we have substantial day-to-day variation, and if we force, so we restrict randomization such that we have one healthy and one disease on each day, we can now make comparisons within each day, and these comparisons will essentially be less affected by between-day variation, right? So it turns out that we can do it exactly the same way statistically. Again, how statisticians think about that. We will also write a more complicated model, which will say now we have differences between the groups, we have deviations between the days or between plates or between whatever it can be, right? Then we have biological variation, we have technological variation. We can write out the variance of our signal from this particular design, and this is the variance that happens if we just randomize across all the days and do not restrict randomization to days, and we can write this variance if we restrict randomization. And you can see that now this variance lost this variance of the block, so day-to-day variation, which is a good thing because now this reduced our variance. And so in terms of planning experimental design, what I would do is to say, well, we have a choice, right? Because clearly blocking is more work, right? We need to remember to randomly select for each block and so on. It's much easier to randomize. Is it worth it or is it not worth it? Well, it depends on how much day-to-day variation we have in our study. If it's a lot, then it's worth it. If it's little, then it's extra work and it's not necessarily helpful. And so this is what we can see. So this green bottom line here is what happens if we actually restrict randomization to the days. And these two lines on top depend on small block variation or large block variation. And so now we can also make graphs like that to decide if the extra blocking and manipulation with our samples actually is useful in terms of reducing variance or not. So but again, we need to know how much day-to-day variation we have, so we need to have pilot data to characterize that. And so same thing, right? So now we have this new type of variances, right? And we will again bound it by this quantity and solve, for example, for the number of biological replicates. And because variance here is smaller, it will require fewer biological replicates. So mathematically, this is what happens, right? And this is why we need to know a lot of things about the experiment to really be effective in terms of how we can design the experiments. Okay, and of course, we didn't really spend much time talking about this. We will talk a little bit, we'll touch upon TMT next week, but let me just bring it up. So of course, a really big kind of component of experimental design is labeling, right, in mass spectrometry, where we try to label samples from multiple sources and pull them together so that we can acquire them simultaneously within the run, because this allows us to reduce run-to-run variation, right? But this can have other issues, including cost, including interferences, so there are also kind of trade-offs. And we can actually consider the advantages or disadvantages of these designs from the statistical perspective. So if, let's say we have 5 groups, and let's say we can have a TMT with 5 channels, meaning that we can have one sample from each group mixed together in one run. So here block is one run. We have one sample from disease group mixed together, and then we have additional blocks. So this is a really good kind of a situation. But what if we have 5 groups but only 4 channels? So now we have a problem, right? Because with 4 channels, we cannot put 5 groups in one run. So we need somehow mix and match. And so again, I don't have much time to tell you about this, but just as a highlight that there's a lot of statistical methodology that goes into this type of problems. And so a while ago, Ann Oberg and we wrote a review which actually discusses this type of thing, so you can take a look. So there are allocations to allocate 5 groups into a small number of channels which are more effective than others. And by effective, I actually mean, again, the variance that we obtain in our signal, right? So we essentially can minimize the variance in the signal by allocating the groups in a smart way. And so here, this smart way essentially involves balanced incomplete block design. So it's a rule where you have, in each run, you always have a different group missing. So you see that this missing group kind of varies from one run to another. So that you always have different subset of samples in the block, and always different sample is missing. And you can do this even worse. Like, for example, let's say you have SILAC, you can only have 2 labels, right? So you can actually do this like that. So now, again, you can have a systematic way of allocating samples from 5 groups to different SILAC labels to minimize the variance. And usually, if you have many groups, what people do, for example, with SILAC, they will have some kind of reference mixture, right? And they will compare everything to the reference mixture. And for different types of experiments, we can compare different allocations and see which of them minimize the variability. So, and the variances will have formulas for this, and it's actually in our review. So this is what I'm saying, that at that point, it requires more statistical expertise to actually work it out. But especially for large-scale experiments and for experiments with complicated designs, there is really a lot of value in doing that. And we kind of now exploring this for things such as TMT in particular. Okay, in the last 4 minutes that I have, let me also answer another question, which is also very common. How about pooling? When you have a lot of samples and you want to minimize the number of runs, is it a good idea or not? And so pooling essentially means you mix together samples from multiple individuals and then acquire them together without any labeling, right? And the question is it a good idea or not? Well, let me give you one example. So let's say you have 2 groups, healthy and disease. You have 10 replicates from healthy, and then you have 10 replicates from the disease. You pull together all 10 in healthy. You pull together all 10 from the disease. You have 2 mass spectrometry runs. Is it a good idea? It is a bad idea because we lost all information about variation, right, by averaging samples completely. What we can do instead, let's say we have 10 replicates, well, we can have 5 pools of 2, and we can have 5 pools of 2. This is better now, right, because we still have the information about biological variation, right, but we reduce the number of runs. So it turns out that, at least theoretically, this is actually a good thing. So, and how do we know this? We do it exactly the same type of thing. We do calculations based on the signals. And so it turns out that if you just have, let's say, 10 mass spectrometry runs, and each run is one subject, so you have this type of variance. And if you have 10 mass spectrometry runs and each sample is a pool, the variance is like this, and R is how many biological replicates are within each pool. So we see that the pooling for a fixed number of mass spectrometry runs, if each sample is actually full of multiple biological sources, you can show that you can reduce the variation, at least theoretically. So there are some practical aspects of this which may not be desirable. For example, if you have a mass spectrometry run, a failed mass spectrometry run, so now you lost more biological replicates, right, because they were all in that run. So there is more opportunity for loss. If one of the samples in the pool was compromised, the entire pool is compromised. So this is also not a good thing. One more limitation of that is that it limits what you can do with this data. So remember statistical goals in the beginning, right? And I said comparing averages versus predicting the status for individual subjects. So you already averaged the biological material. So now you are bound to make conclusions on averages. So pooling is not really appropriate for biomarker discovery when you want to predict the status of an individual subject because you're working with average subjects already by pooling them. So some thought needs to go into what type of analysis you want to do before designing this experiment. But generally speaking, it's actually not a bad thing. And I wanted to tell you a few words about assay calibration, but let me maybe stop here because we're just in the break. But you can take a look at the slides, and if you would like to know more about that, maybe next week or so, let me know. Maybe I can include this in some of the slides for later. Okay, let me stop here, and if you have any questions, I am around.